Hi, welcome to video 4.2/4.3a. I'm going to kind of do these together. So the first thing I want to do is look at calculus in motion to show you an example of what I'm talking about here. So we have this area, this region, this shaded region, bounded on the top by this blue polynomial curve right here. On the bottom by the x-axis, on the left by a vertical line, x equals, looks like -2.5, on the right by x equals b. And we're going to approximate that area using a Riemann sum, which is a sum of rectangles. So what I'm going to do is I'm going to show you, double click, and I'm going to show you how I'm going to start with, say, 3 rectangles. Okay? So I'm going to show you what are called left endpoint rectangles. All right, so that would give me a pretty good approximation. I know how to find the areas of rectangles. I do have some underlap here that I'm kind of lost out on, and I've got a little bit of overlap. But what's going to happen is if I change that 3 to, say, 6 rectangles, oh, that's a better approximation, less overlap and underlap. And now we'll watch what happens as we keep making more and more and more rectangles. You can see that the skinnier that our rectangles are, the smaller and smaller the overlaps and underlaps become. And if I was, you can imagine, now they're going to go to, they're going up to 80. But you can imagine if I went to 800 or 8,000 or 8 million or 8 billion, you can see how the underlap and the overlap are just disappearing, disappearing, disappearing. Okay? All right. If I want to show you, oh, I stop now. Okay. Hide integral shading. I don't want you to hide integral shading. We need to stop now. Stopping. Okay. Hide those. Hide those. Okay, so so those were left rectangles. So let me show you again. Let me just start at 3. Okay. Why didn't it show you one? Okay. So you'll see the rectangle, at the height of the rectangle touches the curve at the left side of the rectangle, at the left side of this rectangle, at the left side. You could also do right rectangles. Now the height of the rectangle goes up to the right side of the curve, okay? So if you took this interval from here to here and you went up to the curve here and up to the curve here, you'll notice this one's on the left side, this one's on the right, so that's the height that we take. There's also midpoint, which is halfway between. So halfway between here and here is this, and that's where we take the height. Halfway between here and here is here. That's where we take the height of our rectangle, and halfway between here and here would approximately be there. Okay, so that's where we decide to take the height. All right, so basically, Riemann sum is a sum of the areas of rectangles to approximate the area bounded by a curve, the x-axis, and 2 vertical lines. Okay? The distance, and most of the time, not always, but 95% of the time, these rectangles are going to be evenly spaced. They're going to have equal subdivisions or equal intervals, which means all these dx's and delta x's are all the same. Okay, so it's going to be a Riemann sum is the sum of the areas of rectangles, usually with equal width, and that'll give us an approximation of the area of the region. Of course, if we were to let the number of rectangles go to infinity, the area of the region would be exactly, and how this is what we're doing, the width of each rectangle, if you come back up here, is your delta x. The height of each rectangle, depending on which rectangle you're out, is f of your x. And I'm adding together all of those areas of rectangles, which is width times height, and I'm doing that as n goes to infinity. Okay, and that symbol, all of this stuff is symbolized by the integral, and this is where I was telling you the definite integral ties into area. Okay, so this says later, we already did this. This was 4.4a, evaluating definite integrals, and as it turns out, the answer that we get is actually the area bounded by y equals x squared the x-axis, the vertical line x equals 1 and the vertical line x equals 5. Okay, so you're going to be given the number of rectangles. It's not up to you to guess how many rectangles you're going to be using. You'll be told whether they're left endpoint, right endpoint, midpoint, inscribed, or circumscribed. Usually they'll tell you they're of equal width. Obviously, if I'm going, say, from 0 to 10 and I have 5 rectangles, then the width of each one is 2, which is 10 minus 0 over 5. Okay? There is a worksheet on this. We'll come back to that later. Approximate the area bounded by these things using 4 circumscribed rectangles of equal width. Okay, so you're going to want to draw the figure. Here's y equals the square root of x. Here's the x-axis. Here's x equals 3 over here and x equals 11 over there. So we're trying to approximate this black area, which is the area under the curve above the x-axis and bordered on the left by x equals 3 and on the right by x equals 11. So the first thing we're going to do is we're going to need the width of each rectangle, which is our delta x, which is b minus a over n. I went from 3 to 11, so 11 minus 3, I went the distance of 8 from 3 to 11, and I want to split it up into 4 congruent rectangles of equal width. So I take that 8 and divide it by 4. So that started at 3, plus 2 is 5, plus 2 is 7, plus 2 is 9, plus 2 is 11. Okay, so we're going to add the areas of the rectangles. Now, of course, every one of these rectangles has a length of 2, so I'm just pulling that on the outside. Now, these happen to be circumscribed. Now, circumscribed in this case means left endpoint. It means on each interval, you're going to have to find the highest spot. Well, that's at the right. From here to here, highest spot at the right. From here to here, highest spot at the right. Same thing over here. If the function's increasing the whole time, obviously circumscribed will be the same thing as right endpoint. So the height of each rectangle is 2. The width of each rectangle is 2. The height of the first one is f of 5. The height of the next one is f of 7. The next one is f of 9. Well, f of x is root x, so that becomes root 5 plus root 7 plus root 9 plus root 11, which would be approximately 22.9397 if you rounded it to 3 decimal places. Okay? Okay, so Riemann, which is rectangular, ooh, look, they both start with R. Riemann sums to approximate the area bounded by a curve, which for now will be above the x-axis, also bounded by the x-axis on the bottom and 2 vertical lines on the left and right. You will be told to use your Riemann sums. You will be told how many rectangles, usually of equal width, and you'll be told which type of rectangle, left endpoint, right endpoint, midpoint, inscribed, or circumscribed. So here's another one. This time bordered on the top by f of x equals x squared, left border x equals -2, right border x equals 3, bottom border x-axis. It's telling you to approximate it using 5 inscribed rectangles, again of equal width. Okay, so here's our curve, y equals x squared. Here's our left border, x equals -2, our right border, x equals 3. So we're trying to approximate the blue area. Equal width, so the width is b minus a over n, which is 3 minus -2 over 5. So to get from -2 to 3 in 5 equal steps, I'm going to have to go up by 1 each time. So label those spots. -1 plus 1 plus 1 plus 1 plus 1. Now they wanted inscribed, which is the lowest height. So let's start with this interval. Here, obviously, the lowest height is here, which is the left endpoint. Same thing between 1 and 2, the lowest height is at 1. Between 0 and 1, the lowest height is at 0, which means there's no area there at all. If I come over here, now because the function is decreasing, the lowest spot will be at the right endpoint, and same thing here, which is again at 0. And therefore, I'm going to add these 5 rectangles together to get my approximation. I have 1, which is the common width, so I'm just pulling the width out in front since it's width times height plus width times height. And my heights are at f of -1, f of 0, f of 0, f of 1, and f of 2. I use f of 0 twice because in this interval, 0 is at the lowest height, and also in this interval. Okay, our f of x was x squared, so -1 squared, 0 squared, 0 squared, etc., etc., etc. And our approximate area that we get is